In 1909, a brilliant young physicist fired alpha particles at a thin gold foil and saw the impossible. Most alphas streamed through as expected, but every few thousand, one bounced almost straight back. Today, we'll uncover how Ernest Rutherford and his team turned this startling result into the discovery of the atomic nucleus. This is Ernest Rutherford with his team, 1910. Young Geiger, Front, and Marsden would be the first to record those surprising alpha deflections. Their gold foil experiment overturned the old atom model. At the time, J. Thomson's Plum Pudding Model, 1904, was widely accepted. The atom was pictured as a diffuse cloud of positive charge with electrons embedded like raisins. Classical physics predicted alpha particles should hardly notice this spread-out charge. Large deflections were impossible in that model. The apparatus was simple. A radium-derived source emitted high-speed alpha particles, about 2 × 10⁷ meters per second and 5 megaelectron volts. They were collimated into a narrow beam by a slit in lead shielding. Ahead of it sat a piece of gold foil, a foil only a few thousand atoms thick, 10⁻⁵ centimeters, milled to be as thin as possible. The whole assembly was kept in a vacuum chamber to avoid air scattering. On the far side of the foil was a movable zinc sulfide screen that flashed with each alpha impact. A microscope outside let a researcher count tiny scintillations one by one in the dark. For detection, Geiger and Rutherford had built a sensitive setup, an evacuated tube, right, with a zinc sulfide screen and microscope. Each alpha that hit the screen produced a tiny flash, counted by hand under the microscope in a darkened room. They could rotate the detector around the foil to measure scattering at different angles. Early on, Geiger and Marsden would sit in darkness, eyes adapted, scanning for flashes. Their quote from 1911, "Our tube worked like a charm. I could count at intervals for a whole night without disturbing my equanimity." After weeks of counting, the picture emerged. Almost all alphas passed straight through the foil, as if it were almost transparent. Only a thin curtain of gold atoms was encountered, so most paths remained undeflected. A few alphas were slightly deflected, a few degrees. This was understood as grazing interactions with the weak positive cloud, or multiple tiny scatters, still consistent with an empty atom. Shockingly, a very few alphas were deflected by large angles, tens of degrees, even back toward the source. Rutherford calculated that for gold, only about 1 in 20,000 alphas were scattered more than 90 degrees. Rutherford's bold conclusion: every atom must have a tiny, massive nucleus carrying all the positive charge. The size scale, alphas came within 10⁻14 meters of the nucleus before rebounding, while atoms are 10⁻10 meters across. This nucleus is thus 10,000 times smaller than the atom. In other words, more than 99.99% of the atom is empty space. This explained the observations. Nearly all alphas miss the tiny nucleus and pass through. A few skim past and curve slightly, and an extremely rare one hits nearly head-on and is flung back. In his 1911 paper, Rutherford wrote that the data seems simplest to suppose that the atom contains a central charge at a point. He did not even use the word nucleus, he called it a charge concentration, but this was the birth of the nuclear atom. The 1911 nuclear model was revolutionary. Thomson's venerable plum pudding atom was laid to rest. As Britannica notes, Rutherford showed the atom was mostly empty space. However, Rutherford's model was classical. It could not explain why orbiting electrons don't radiate themselves into the nucleus. It did not explain atomic spectra or stability. Those puzzles were solved by quantum theory in the 1910s. Niels Bohr proposed quantized orbits in 1913 in Rutherford's lab, and later Schrödinger and Heisenberg the quantum atom. Also, the nucleus itself was incomplete.
Rutherford assumed only protons, electrons balanced out elsewhere, but in 1932, Chadwick discovered the neutron, completing the nuclear picture. From Rutherford's lab in Manchester, we learned the universe is built around tiny, heavy hearts of atoms. As Rutherford himself said, "We have found the one central thing, the nucleus, which was out of reach to early ideas." The gold foil experiment reminds us science can change everything with a few surprising sparks. In the end, the atom turned out to be almost empty space with a dense nucleus at its core, a discovery that forever changed our picture of the world.